everyone. Thanks a lot for joining this month's community meetup. Today we'll be deep diving into the new Postgres Direct Source that shipped with Materialize 0.8. Joining you from Materialize today is me. I'm Marta. I just recently joined Materialize as a senior developer advocate. And on the other side, we have Petros, who is a member of the technical staff and one of the core developers behind this new feature.
Hey, everyone.
So we'll start with a short intro to this to the new Postgres source, and then Petros will walk you through a demo so that you can see how it works in practice. And as we go, please drop questions in Zoom. And please, if you remember, use the Q&A functionality instead of dropping the questions in the chat. It makes things easier for us to manage. And then we'll get to the questions during the presentation. All right, I'll hand it over to Petros now.
Thank you, Marta. Hey, everyone. Let me just get my screen share going. Okay, can you all see my screen?
Yep.
Okay. Right, so today we're going to talk about the Postgres Direct Source, which is a new type of source that was added to Materialize. And we're going to see how the design works. We're going to see how the user experience looks like, what the users have to do to set it up. And then after we go through all that, in theory, we're going to move on to practice, and we're going to do a live demo where we're going to use this source to make a real-time dashboard. But before even starting with the Postgres source, I just wanted to say a few words about Materialize itself in case you have recently heard about it. So Materialize is a SQL streaming database. And what it allows you to do is to define materialized views in SQL, and Materialize will incrementally maintain that. What is particularly interesting for this kind of audience here, which I suppose has some experience with running Postgres in production, perhaps, is what differentiates, like why would you want to define your materialized views in Materialize? Or perhaps why not use some other streaming product to do your streaming workloads? And then the answer to this question is that usually there is some kind of trade-off where if you want to have very expressive ways of defining your computation, then you're looking at SQL, and in SQL you can do complicated things like multi-way joins, aggregations, and subqueries. But once you go there, your only viable option, if you're using Postgres in this case, would be to have a materialized view that you refresh manually. And so you're bound to have a big latency and a recomputation of the view. On the other hand, you can certainly consume the change data capture stream out of Postgres. There are things like there are projects that can export that into a JSON stream for you, and you can do some computation based on that. The trade-off you're giving up there is it's very hard to do complex computations. And so the Materialize is the answer to what if you want to have both. So it allows you to have arbitrary SQL, and it will automatically figure out how to incrementally maintain those views, which usually gets you to sub-second latency up-to-date views. So Materialize is a general database that gets data from what we call sources. And today we're going to talk about a particular type of source with the Postgres sources that allow you to connect directly to a Postgres database as if Materialize was a read replica. So we're using the same protocol that Postgres itself uses when it does replication, namely logical decoding. And that allows us to have very direct and a very good quality stream to work on. And we're going to see in detail what that means. Some details about this feature. It was introduced in version 0.8 behind the experimental flag. and it is going to be stabilized in Materialize version 0.8.2. So that is going to be released in 1 or 2 weeks. And after that version is released, you will no longer need to run the experimental flag. And the other important thing is that the logical replication is something that you can use not just with a Postgres database that you're hosting yourself. You can use it with popular cloud offerings. I have listed 3 here that we know support logical replication. So if you have an RDS, or with the Postgres variant or Google Cloud SQL, you can certainly connect Materialize to one of these things and get running. So if you have used Materialize before this feature, you probably know that there was a way to consume data from Postgres. And I just wanted to present it here as sort of the motivation behind this feature. Before direct Postgres source is your only option if you wanted to consume a Postgres data was to first get them into a Kafka cluster. And the way you do that is by running a project called Debezium that itself reads a replication stream, just like Materialize does today. So Debezium would read the replication stream, fan out to one Kafka topic per table, and then Materialize was able to read back all those Kafka topics and reconstruct the structure of the data. The problem here is that many companies just have a single Postgres database, or they might not have experience with running complicated Kafka clusters or a Zookeeper cluster. And it was generally a hard proposition, a difficult proposition to run all this infrastructure just to get some data into Materialize. And so that was the motivation for the initial development of this feature. And this is what led to this kind of architecture where Materialize can directly connect to an upstream database. Once Materialize connects to an upstream database, I mentioned before that we're using the logical replication type of stream. And this is a particularly good setup for Materialize because the stream contains all the data that changed every time there is a transaction on the upstream database that change rows. We get the transactions in commit order on the stream, and Postgres itself will take care of de-interleaving in case there are concurrent transactions. And so we get back a very clean stream that just says, here is the beginning of a transaction, these things changed, then there's a commit, then there's another transaction, et cetera, et cetera. And this allows Materialize to guarantee correct results downstream. And by correct, I mean that if you have a Materialize view on with a very complicated query with joins and all these things, as the data is being streamed into Materialize, you will never see a result in your Materialize view that couldn't have possibly happened. If you see something, it means that there has been a state in the upstream database that would have produced this result if you were to run the query at that particular time. And so this is a very strong guarantee. And of course, because the connection is direct and there are no other computers in the middle, there is no cluster, there is very low latency, usually in milliseconds. So picking a bit more into what happens when we ask Materialize to use replication, is that the Materialize, once connected to the upstream database, can start replicating the data of our selected tables. We're going to see how to do that. But the important thing is that the replication is happening in 2 parts. So if you imagine in your head the transaction log advancing in time, when Materialize, when you actually type the create source command, there will be a point that replication will start. And so from that point onwards, we get all the transactions that happened. And Materialize has logic that it can do a bulk copy of everything that was in the database before that point. So you connect at time 10, let's say, we do a bulk copy of everything up until that point, and then we atomically switch to reading the stream. And the method is such that there's no way that we lose some data in between. And this again speaks to the consistency guarantees that Materialize gives. And so again, there's no way you would ever observe maybe half of the bulk copy done and get real results. You either see everything in a consistent state or nothing at all. To use the feature, there are some requirements that you have to fulfill on the upstream database. And I've listed three important things here. So the first is that Postgres must have logical replication enabled. That's something that's not enabled by default. And the way you do that, if you're running Postgres by yourself, is by setting the well level parameter to logical. And then for cloud products, there are equivalent ways of setting this parameter through for example, RDS has a particular parameter that ends up tweaking the well level. The other requirement is that all the tables need to have their replica identity set to full. And the third one is that you cannot have toast columns. And for those ones that are not familiar with toast columns, that all that means is that if you're storing text, it can have a maximum size. And we have documentation for all of these and what they do. And I'm going to explain some of these once we go through the demo and actually set this up. But in general, this is a fairly low constraint to add to your database. So these are the requirements for the upstream database. And the other thing I would like to mention about the upstream database are some concepts that, again, might not be you might not be familiar with if you're using even if you're using Postgres. So if we imagine a Postgres database, the Postgres database has a hierarchy of objects. So there's a database. The database has schemas, and schemas have various different objects. In this case, we're only interested in tables. And so I've depicted that here with two schemas, schema A and schema B, with a bunch of tables. One new object that is relevant during replication is what is called publication. And the publication is essentially a named object, so you can do create publication and give it a name. And with the publication, you select the tables that you wish to replicate to another database. And this is because you might want to use Materialize to compute some aggregations over some hot table, but there are other unrelated tables that you don't really want to transfer over the network or do any computation on them. And so using publications, you have the opportunity to filter out and select the tables that you want to participate in your replication. Again, we're going to see that in detail once we set it up in the demo. And just here in this diagram, this publication foo consists of table 5 and 6 from schema A and table 5 from schema B. The other term that you might hear throughout while working with this feature is a replication slot. And a replication slot is, again, an object that will be created by Materialize inside the upstream database. So Postgres will hold the replication slot. And the replication slot represents where Materialize is in its replication in terms of point in time. So if we go back to this diagram, and you imagine this blue arrow moving forwards, the replication slots will record at any given point up until which time Materialize has successfully synced. And this is what allows the this is what allows Materialize to recover and resume replication. For example, when a connection drops, it can use the replication slot to restart. And then one important point about the replication slot is that from the moment it gets created, it will hold up the necessary data for the system that uses the slot to resume. And this is important because if you start Materialize connected to a database, which will create a replication slot, and then you I don't know, delete the EC2 node that you were running Materialize on without taking care of properly dropping the source and leaving a replication slot around, this is something that will start accumulating space on the upstream database. I won't go into too much detail. Again, this is something that is covered in our documentation and what you can do to manage these slots. But just know that this is an object that will be created automatically. Okay, so imagine now that we have our Postgres database, which we have set up with these parameters here. We have a publication. Now let's go over to the Materialize side and see what it looks like to use this source. And so using this source is fairly straightforward. The syntax is what's shown here on the screen. So you can do create Materialize source, you give it a name from Postgres, and it needs two parameters. The first parameter is the connection string. It just says the username and password and where the host of Postgres. You can also optionally use TLS certificates. And the other parameter is the publication name. So here would be foo, for example. And this is how Materialize knows, what things do you want to, what things this source will end up having. And I have here an example to see what happens after creating a source. So let's say we had two tables, users and users like fruit on the PostgreSQL side, and we created the source here. What we're going to end up on the right side is this odd-looking table. And this odd-looking table of the source contains one row for every row of the tables in the publication. And the rows are tagged with the table ID. So here we see users happen to have table ID 50, so we know 50. And then in the row data, it's just a text encoded array with the data. So this is how Postgres sends the data over the wire. So this is what this table represents. But this is pretty hard to work with. Like, we've lost precious information in this kind of format. We don't have the table name, we don't have the types of the columns, we don't have the names of the columns. So it's pretty difficult to work directly with this kind of table. And so if we wanted to enrich this structure here and get into a place where we have a separate object for users, in this case, and a separate object for user likes fruit, what we could do manually is define some views over this raw stream that bring back these things that we've lost. So for example, I could say create view users as this select from the source name, which is the raw data, and I just filter by the table ID that I know users had the number 50, and then I can do my name assignment and my typecasting here. And similarly for user likes fruit. But this is pretty tedious and nobody really wants to be writing these kind of views. And so there's another syntax that got introduced with this feature, which is the create views statement, views with an S in plural. And what you can say to Materialize is create views from source and give it a source name. Currently, the only type of source that supports this create view statement is Postgres. And what happens when you run this statement is that the Materialize will actually go on the upstream database, introspect the publication you've given it, get all the tables that are participating, their names, the column names, and the column types, and automatically generate these tedious views for you. And the first variant of this, which is the simplest, will just go and create one view per upstream table. If you would like to do only specific ones, you can definitely list them in brackets and even rename them if the table in the upstream database happens to have a name conflict with something that already exists. So after you've done essentially after you run these two statements, the create source from Postgres and give it the connection parameter and the publication, and then run the create views command, what you end up with is one view per upstream table that you can query as normal. It has all the data. It will be automatically updated from that point onwards. And this is the point where you can start thinking about what Materialize views you'd like to build on top of it. And this is what our demo is going to be about today. So before moving on to the demo, I'm going to pause here for any questions that happened during this first part.
Yeah, so there's a couple of questions, actually, some of them coming in right now. Maybe we can start with two related questions about the size of Postgres tables. So the first question is, can Postgres table sources be larger than in memory / is there a limit on how big the Postgres tables can be? That's
a great question. So something that I didn't mention here, currently, yes, there is a limit, and the limit is related to the fact that today you are forced to materialize the Postgres sources. So here, normally you can say create source from something else. With Postgres, you're forced to materialize that. And what that means is that because you're going to materialize the row replication stream, it means you have to have enough RAM to hold on all the data of the publication. This is something that we're working on lifting, and once lifted, then there's not going to be any limit. So for example, if you had 1 terabyte, a table that was 1 terabyte, and you just wanted to compute an aggregate, I don't know, maybe an average of something, then you would certainly be able to do that without storing everything in the materialized memory. But for now, yes, this is a limitation, and you have to have enough RAM to hold your data.
Okay, so second question is about restarting Materialize. If it always, I think you touched on this when you talked about replication slots, but just to make it clearer, maybe. When you restart Materialize, does it always replicate all the tables from scratch? Does it matter if it takes hours or days?
Yeah, so right now Materialize doesn't have any persistent storage. So if you shut down Materialize and restart it, and this is regardless of the type of source, all sources will start again from the beginning, and this is the same for Postgres. So if you have a huge database that takes days, then unfortunately you will have to wait days if Materialize crashes. So this is something that this limitation is going to be lifted like across the board for all sources once we have persistence, which is it's pretty tricky to implement, but we're working on it.
Okay, so next question, since Materialize uses Postgres replication streams, if it fails to consume data quickly enough, can it cause congestion in the upstream Postgres database and eventually, potentially taking it offline? So what steps does Materialize take to guarantee the stability of the upstream database?
Yeah, so once a replication slot is created, the upstream database will keep data around to ensure that the downstream database can always resume. And so if it happens that Materialize is not able to keep up with the replication slot, then the upstream database will be holding on to more and more data. And eventually what's going to happen is run out of disk space. And this has been a big pain point in Postgres. Materialize itself doesn't do anything to prevent that, but fortunately, there has been a solution in Postgres itself. So if you're using Postgres version 13 or above, there is a parameter that you can set that sets the maximum amount of data on disk that the replication slot can hold. And so you can set it on a safe limit for your setup. And once, if it happens that the replication slot falls behind and hits the limit, then the upstream database will just start recycling, and then you will start getting, you will not able to continue replication from Materialize. So that's something that's definitely something that's advisable for production setups if you use Postgres 13.
Okay, thanks. We have 3 more questions. So
okay.
After the initial views are created, are upstream schema changes handled automatically? And I think also related, what's the suggested way to apply a DDL?
Yeah, so after the initial creation of the source, no changes are replicated. So for example, so the things, so changes that change the schema of the upstream table. I guess the accurate thing to say here is that if you alter the schema of a table upstream, the raw data in the source will be successfully, like you will start seeing new data. So for example, if you added a column in the users table, you would suddenly see 3 things in the stream. The problem is that the downstream views, first of all, are not reactive to that, and second of all, if you happen to change the type of the column into an incompatible type, then you would start getting errors. And so I think the answer here is that you need to have some sort of tool that manages DML changes similar to how you would have you have to handle that with Postgres itself. So Postgres itself, again, if you're replicating a Postgres to Postgres, does not handle that. You have to coordinate your DML changes, and with Materialize, that would probably mean tearing down your source, doing the DML changes, and then reinstantiate them. Should we postpone the other questions for the end? Maybe I'm just looking at the time to go through the demo.
Yeah, sure. We can keep the last one for after the demo.
Great. Okay. So for the demo, what I would like to show is this is the plan. So we're going to take a vanilla Trello-like web application called Planka that is just a simple Node.js service backed by PostgreSQL. After this is up and running, we're going to add Materialize to that and set up the replication. So we're going to go through the steps that I showed before. Then we're going to define an interesting view on its data. We're going to do some joins, some aggregations, and finally live stream the results into a React web dashboard. So we're going to see how, in the end, what we're going to see is that as I change things in the Trello application, the real-time dashboard changes pretty much at the same time from data flowing through Postgres to Materialize to our dashboard. So this is a diagram of what we're going for. So I'm just going to switch to my terminal now to get started. So I mentioned we're going to use a pre-existing application. This is a Trello board, open source Kanban board, and we're just going to go in its GitHub page and grab the compose file. And I'm going to switch to my terminal. And for now, we're just going to download it and start the application to see what this is about. So it's a very simple project. It just has a, do I have it running somewhere? No. It's going on. Sorry, the demo gods have failed me. Oh, I think I know. Okay, I had a previous version of it. Okay, so I just start the demo, and then if we look at the project here, is the Trello board, and let me just create a project here and add a few data. So say Materialize webinar create a board Postgres sources, and I'm just going to do a simple icebox to do in progress and done. And then I'm just going to add present Postgres sources. Okay, so this is the application that we are interested in grabbing some data out of and using them in Materialize. So let's go install Materialize in the Docker Compose. So what we're going to do here is, first of all, if you remember from the slides, we need to add the well level parameter to Postgres. So I'm just going to pass that here. That will enable logical replication, and I'm just going to expose the port of the database to my local machine so that we can connect to it. And then also we want to run Materialize. And I mentioned that the Postgres sources are going to be stabilized on version 0.8.2 that is not released yet. And for this reason, you have to excuse me for that, I will use a nightly image, but if you're doing it from the future, you can just use any version above 0.8.2. So we just grab this image. Again, I want to connect, I want to forward the port of Materialize to my host that we can connect. And that's about it. So this is all I need to do to run Materialize in this cluster. So if I do Docker Compose app again. What did I do? The demons again. Cannot start network not found. Oh, I see there is some leftover state. Sorry, I have to. Sorry about that. Okay, so what happened is that I restarted everything, but that means that I will have to recreate these things here. So let me just do it quickly. Demo, Postgres sources, and then box to do in progress. Done. Okay, and this say present PT sources. Okay, so we have Materialize running now. And so the next thing we need to do is create a publication in the Apsum database and set the replica identity to the tables that we're interested in to full. So let me just connect to the database. And here we see we have a bunch of tables. If we have created a card, if I select from it, we can see the name present PT sources. And the tables that we're interested in for this demo are the card that has a list of cards, the card label that has the labels, label here. List is the list that the card is currently under, so in progress, down, to do, etc. And also attachment, which will hold files that are associated with the card. So let me just alter table card and set the replica identity to full. And I'm going to do the same thing for the rest of the tables that I'm interested in. So label, list, and attachments. And so now that I have set the replica identity to full for the tables that I'm interested in, I'm going to create a publication. I'm going to name it Planka. And the tables that I want to have in that publication are cards, card label, label, list, and attachments. So now there is a publication, which means that we're ready to go on the Materialize side and create a source that will replicate the data that I have selected here. So let's do that. So I'm going to connect to Materialize now. And let me just do it here to show it more clearly. So create materialized source. I'm going to name it Planka again from Postgres. And I need to supply the connection. So that would be Postgres. The host is Postgres because it's running in Docker Compose. And the database is called Planka. And we want the publication also named Planka. Finally, I want to add an option here that is available for all sources in Materialize that tells it how often it should timestamp the data. Because in this case, I'm interested in a fast, a low latency, and having a quick reaction from the moment I do things on the one dashboard and appearing on the other one. I will set the timestamp frequency to 100 milliseconds. So I created my source, and now if I select, we can see that Materialize has synced some data here. And you can see that we have 4 things from table 1646.7, which are the list to do down icebox in progress, and we have 1 card. And again, this is not super convenient to work with. So I'm going to create views from source, Planka, which is the name of the source here. And after I've done it, if we inspect the current views on the system, we see that we have 1 view per upstream table. So now I can just select from card and see the exact same data on the Materialize side that was available on the upstream database. And of course, let me just select the name. If I go change something, so let's put an exclamation mark here. If I go here, the exclamation mark has been set. Okay, so now we have set up Materialize to grab all the data from Planka, and we're ready to define some interesting views and compute something. So let me just open a second editor here, and so that we can see what's happening. Let me move myself around. And so what we want to do here, let's start simple. I'm gonna say create or replace, because we're gonna work on it incrementally. Create or replace materialized view, and let's make a card summary. So this view is gonna have some summary about the cards on the system. So for now, I'm just gonna select some attributes of the cards that are interesting. So the ID, the name, and the description from card. So we start simple. So let's instantiate this view. Go here. So now we have the card summary view, and if I select and see what's inside, we see that we have what we needed. So to showcase the what I said in the beginning, that you can define arbitrary views with joins and aggregations, let's get some related data from these cards. So one of the first things that we want to join with is the list that this card is under. So let's just join with the list table. And the reason I have to qualify with public.list is because Materialize has a data type called list, so I need to disambiguate it. And we're gonna join on card list ID equals public list ID. And let's get the name of the list and put it in our results. So list name. So now if we replace this view and select again, we can see that we know that this particular card is in progress. And what we want to what we want to sync is the ID, the name, and the description. We want to know the list that a card is at. We want to know the list of labels. So let's say I say this is urgent and add the label to this card. We want to know that this card has this label. And finally, a card can have a cover picture. And so if I upload this cute dog here, we want to know the file name of this picture as well. So let's go do that. So the first thing is to get the cover picture. To do that, I can do a left join attachment. And it's a left join because there might not be a cover picture. So we can just say on cards, cover attachment ID equals attachment ID. And what we want to take from this attachment table, if we look what is in there, if we look what is in the attachment table, this is the file I just uploaded. We're interested in the dir name and the file name. But what I'm going to do is I'm going to describe a more, I'm going to do some select expression here to make it easier to work with later. So when dir name is null, that means there's no file. So we're just going to set the column to null. Otherwise, we're just going to concatenate the directory name with the file name. So let's concat the dir name, / and the file name. And I'm just going to name that file path. So that's our new view. So let's see if it works. Update the view, select from the view. And we see that we have a file path for this particular card. But then finally, we want to take all the labels for this particular card. And to do that, we have to navigate a many-to-many relation. So we're going to join with card label on card label, card ID equals card ID. That's the first part. And the other part is the labels themselves. So this is the label ID equals label ID. So once we join with these card labels, because a card might have multiple labels, this is where we want to do some aggregation. So I'm just going to group by everything with what we have so far. So we have the card ID, the name, the description, the list name, and the file name. So this is what I want to group by. And for the labels, I'm just going to present them all as a JSONB aggregation, which is going to put them in a nice array for us. So let's just say the JSONB aggregation of label name as labels. And if we update the view to name, I just need to prefix it attachments. And attachment. Why does it complain? It's called dir name. Do I have a typo? What is going on? Okay, let's keep the file path for now. So I'm not sure why that doesn't work, but let's move on. And what file name? Right. Okay, so we're just not going to do that part. So we see here now that if I select the card summary, we should have the label. So we see origin here. So that's good. And so let's leave it at that. So this is the, let's say this is the view that we would like to sync to the front end. So let's go do that. For that, so I'm going to leave. So Materialize now is running in the background, and it will keep the view updated. So I'm going to start a new Node.js project, and we're going to write a small Express server that has a static website, and the static website will connect to the Node.js server and read the stream of data. So for that, let me just install 3 things. We're going to need the Postgres driver for Node.js. We're going to need a utility to work with streaming queries, the query stream, and of course the Express server. And just for the interest of time, I'm just going to grab the code for the server, and we're going to take a look at the user interface. It's a bit more interesting. So this is the code that we need to that can connect to Materialize and grab the data. So let's take a look at what this is doing. So first of all, it sets up an Express server that will listen on port 4000, and it has two things. One, it will serve static content over from public directory that we're going to look at. This is our user interface, and it has a single API call. And every time you hit this API call, it will open a Postgres connection to Materialize, and it will start streaming a query called tail of the view that we just defined. So tail is a special, you can think of it like a select, but a select that doesn't end. So when you tail a Materialize view, you're going to get a stream of updates as they happen. And so what we do here is that we tail the view, and for every event that we get on the stream, we write it to the output as an event stream. So the data format of our API is called server sent events. It's a very simple format. You can send essentially lines that are prefixed with data, colon. Then you can put any sort of payload separated by a double new line. So anything like in this case, we just grab the event as it came from Materialize, we stringify the JSON, and we ship it to the front end. On the other sides, we're going to look at the public folder. So I'm going to grab again the index HTML. This is pretty simple. I didn't want to use very complicated build processes, so this is just loading 3 different libraries: React Bootstrap, and Lodash, and Babel here to allow us to use JSX. And we just have a main script that is the thing that is going to consume the stream from this API server. If we then grab the main.js, what we can see here is that we have defined a single React component called app, and the meat of the stream processing is essentially this part here. So what we do here is we use the native browser event source constructor. So this is not a library. This is something that all browsers come with. And this is the protocol I mentioned before called server sent events. So here we're just going to say we want to consume the card summary stream. And for every time we get a new message, we want to do something about it. So once we receive a message, that means that Materialize has notified us that something has changed in the list of cards in our summary. And so what we need to do on the front end is react to these events and make sure that we always have an up-to-date and correct representation of the card summary. And the way Materialize signals to us what happened is by using these extra 3 special columns. There is MZ timestamp, which is about when something changed. MZ diff says whether something was added or removed. And MZ progressed means that there are, you should not expect any more data for that particular timestamp. So what this code does is that we maintain an array of cards that essentially is empty. And every time Materialize says that a card was added, we just update our cards and add that to our list. Whereas if Materialize says that a card was removed, we just filter out, we go in our cards array, find the card that was removed, and we just remove it. This is all we need to do to ensure that cards will have at any given point an accurate representation of the data. And then when Materialize signals that the time has progressed, we notify React that it's time to re-render the UI, and we just give it the card sorted by ID. So with this, what is it? 20 lines of code or less, you're able to get a stream of data directly from Materialize and connect it with React and re-render the user interface whenever something changes. So finally, this isn't really relevant for the purpose of the demo, but I just used React Bootstrap to have a nicer user interface. So I'm just going to remove the image part because that one we removed from the query. But this is all we need to do. So let's run the server and see what happens. So if we run the server here and we go in our browser, let's just open it here side by side and see localhost. Okay, so here we see the rendered card as it came from Materialize, and it has synced the title. We know that it is in progress, and we know that it is urgent. And if I move things around, you can see things are changing. And if I add more labels, for example, let's say low priority for some reason, and then add it, we can see it's pretty snappy. Pretty much everything is being synced. And I can add cards, move them around, and change the related tables. For example, now both are in progress. If I say this is in progress, exclamation mark, this is immediately synced. One interesting thing I wanted to mention about this is that this particular application, Planka, has itself a feature where it can sync data between instances of the web application. So let me just open a second version of Planka here. And we will see that as I move things around, the 2 instances of Planka change, and the same goes for the real-time dashboard. I think what's worth noting actually here is that even though what we see on the right is actually the result of Materialize listening on the database itself, getting these data into an Node.js program and feeding them into the dashboard, the speed of change is pretty much identical. Let me just remove the attachment just so it's clear. It's pretty much identical to the custom implementation. So I think this is all I had to say. I think I rushed a bit the implementation, so I hope it wasn't too confusing, but we're running a bit out of time. So I'm just going to pause here for any questions that happened during the demo.
Thanks, Petros. We are close to, we just hit 11:30, but I think if people don't mind, we can still take 5 minutes for Q&A.
Yeah.
There's around 6 questions, some of them related. And yeah, after that, we can just move to Slack and look and just like, Petros will be around, so you can just hit him up there. Okay, so maybe starting with the most recent questions after your demo, 2 related questions about do deleted rows in Postgres take space in Materialize RAM?
No, they don't.
Okay, and these were the only ones after the demo, so we can go back to the ones from the beginning. The 2 hanging ones were if the Postgres source handles properly all data types in Postgres currently.
So currently, you can sync any data type that is supported in Materialize. Not all Postgres data types are supported. I mean, Postgres has a very long list of some pretty obscure ones. But for most applications that use like non-exotic, I guess, data types, that should work. There are known shortcomings. We have some issues in our issue tracker. If there is a particular data type that you want to use and we don't support, and supporting it would unblock you using this feature, definitely get in touch with us either via GitHub issue or in the Slack channel so we can take a look.
Then the next question is still if there's a way to apply a DDL. So DDL operations.
Yeah, so so the only practical way to apply DDL currently is to you have to tear down the source. There's no real good way of doing it without some sort of disruption. What you could do is possibly migrate the data in the upstream database on separate tables, then and create separate publications, and sort of do a not zero downtime, but less than a quicker update than you would have if you started from the beginning. But this is a difficult problem to solve if you want to have DDL statements that affect currently live Materialize views. For example, one question is what happens with your queries that refer to existing columns and things like that. So this is a problem that we don't really know the answer for now, and the practical option is to recreate everything.
Okay, thanks. So we have one last question. Has there been any discussion of adding support for Materialize itself as a source?
Yes, there has. It won't be through this mechanism. I don't think we plan to offer logical replication as an output from Materialize, but we do want to support a CDC stream that we are able to ingest so that you can connect a Materialize instance to another one. So yeah, this should be possible in the future.
Okay, thanks a lot, Petros, for the presentation.
One last thing to mention just before we leave is that all the code that I showed in this demo, you can find it on my GitHub. It's Petros and then Materialize.
I dropped the link in the chat
great.
for everyone.
Awesome. Yeah. Okay. So if you have any questions, please write them in the Slack community channel, and I'll be around to answer them.
Yeah, thanks everyone for. I should turn my video on. Thanks everyone for attending the meetup. If you have any suggested topics for future meetups that you'd be interested in listening about, you can ping me on Slack. And yeah, thanks a lot for dropping by, and see you again soon next month.
Thank you. Bye-bye.
Bye. Thanks, Petros.